All right, this is Dr. DeShavo, Chapter 11, Part 2. We're continuing with how nerves work. And these same principles apply actually to muscles as well. But just keep in mind we're talking about the nerves for now. So the basic gist with nerves, as we spoke about previously, is that they have ions or charged particles that move down them, sending these neural impulses. There's constantly movement of electrons across the cell membrane, but when we have a nervous signal actually generated, we will change those charges enough across the membrane that if we were to put little electrodes in it, we'd see it peak and then return back to normal. And that peak and return back to normal is called an action potential. So when we send that electrical signal down, ions will move across the cell membrane, and ions, once again, are charged particles, and it'll change the charge across that cell membrane. So when we're talking about this cell membrane, if it's just a cell hanging out, doing nothing, it is at resting potential. And the charge for this is -70. And the general gist of why it's -70 is because we put more positive ions to the outside, specifically those sodium ions. And there'll be less charged particles inside, and the charged particles on the inside of a resting cell are mostly potassium. So they're positively charged cells, but there's going to be more of them put out as the form of sodium, fewer kept inside as a form of potassium, and then there'll be negatively charged ions as well, creating overall -70 in that cell, okay? I don't expect you to know this perfectly. This I teach over like 3 or 4 weeks. I'm trying to give you the general gist. And what you need to know for the general gist is a resting cell rests at -70 millivolts. It's going to have more sodium outside. It's going to have more potassium inside. Okay? If that nerve starts to work, it undergoes an action potential. Okay? Done. That's what I need you to know for here. Moving on to give you a visual. This is a resting cell. So we've taken a cell, which usually is roundish. We could have different shaped cells, but let's just say a round cell. And I've cut this part of the cell membrane off, and we're looking at it here. Okay, so this is just that one little section of the cell membrane. Okay. If you look overall, there's going to be more sodium positively charged ions on the outside, and there's going to be a higher concentration of potassium on the inside, but fewer potassium than sodium. Okay, so you're going to get, because of the negative ions, an overall negative charge on this cell membrane. Okay, it doesn't really show it very clearly there, but you'll have fewer positive on the inside than you will on the outside, giving that cell a negative charge of -70. In general, sodium will be at a higher concentration out, potassium it'll be at a higher concentration in, but overall you're going to have more positive on the outside than the inside, giving the cell a negative charge across that membrane. Okay, and that'll be -70 in a resting cell. Now, there's also pumps, so called sodium-potassium pumps we spoke about previously, and these will be protein channels that'll pass through this membrane. And what happens is they'll push 3 sodium ions out and only 2 potassium ions in to reestablish that concentration of more sodium out and more potassium in. But because it pumps 3 positive out and only 2 positive in, overall it still establishes that negative membrane charge. Okay, I know it's all kind of confusing, but remember, sodium is an arresting cell at a higher concentration out, potassium's at a higher concentration in. If we look at the overall charge, there's going to be more positive out than positive in, giving that cell a negative charge of -70. And generally inside of a cell, we're going to have negative proteins or negatively charged proteins. Outside of the cell, there's going to be negatively charged chloride. I always remember that because sodium and chloride go together, right? They bond together. So you're going to have both of those concentrated outside of the cell. Okay. Do they leak across? Absolutely. Sodium likes to leak in, just like naughty kids. They always want to go where they're not supposed to be. Sodium will try to leak in, potassium will try to leak out. Okay, so this is all a resting cell. Now, if we move into an electrical impulse, specifically an action potential. Now, action potentials are what make nerves and muscles work. Okay, these are the steps. Don't drive yourself nuts. I have a great chart to look at, and actually I think I'll look at the chart first with you and we'll come back to these steps. As long as you get the general gist of this, and we're going to scoot ahead 2 PowerPoint slides. As long as you get the gist of this, I'm good with that. And it's really not that hard, I think, when you look at this chart. Okay, so this is not a resting cell. We just looked at a resting cell that's going to have more sodium outside of the cell, more potassium in. Okay, it's just hanging out. It's got a -70 charge. Okay, for an action potential to work, we start to move ions across that membrane. It's very simple. Sodium ions move in. If we move sodium ions in, we're going to get more of a positive charge. Okay, and the action potential actually comes up and it'll peak just about, it says +40 there. I like to go by +30. Okay, why does it stop there? It's because of the balance of ions. Don't let it blow your mind. Just remember these steps. Okay, so -70 is resting. The cell will depolarize. Sodium ions move in, making the cell more positive. It'll peak at +30. Ion channels that we're letting sodium ions in close. Okay. At this point, potassium channels open, and because they're at a higher concentration inside the cell, they start to move out. And if we move a positively charged ion out of the cell, we're going to make it more negative. And that negative motion will go all the way to -70 and actually overshoot it a little bit, okay? Because those channels are actually just a little slow to close, and then it'll regulate itself back to -70. So once again, resting cell decides, so a nerve decides it's going to fire. Suppose the nerve that goes to my bicep muscle decides it's going to fire. It starts at -70 at resting. The signal comes down the nerve in the form of this action potential. The action potential goes through very specific steps. It is stimulated at 1. Sodium channels open, sodium moves into the cell, and this causes what's called depolarization, which is a positive inclination of this, or because positive ions are coming into the cell becomes more positive. It peaks at +30. Okay, don't worry about the Y because that's a whole different conversation. Okay, so +30. Sodium channels close. Potassium channels open. Now potassium ions leave. They're positive, so the cell is going to become more negative. This process in 3 is called repolarization. That keeps going. It generally overshoots the normal resting state of -70. That's called hyperpolarization because potassium channels are just a little slow to close. And then the cell will regulate itself back to -70, which is a resting state. All this happens, all of these action potentials happens every time your muscles and nerves work. It's just the movement of ions across. What you need to know is the steps and the basic charges. So -70 is resting, +30 is going to be the peak of the action potential, and threshold, which is -55. If you have a nervous stimulation that peaks it enough to -55, you will have an action potential. So at this point, it's all or nothing, -55. And the reason you need to know that is because cells are not permanently in the same charge. They don't stay at -70 all the time. As you can imagine, ions will leak in, they'll leak out, they'll leak in, they'll leak out. So the difference between this little bump here and an action potential is when it's actually reached -55, you will have an action potential. Okay? Whew. All right. That's a chunk of change. So please email me if you have questions. But let's go back 2 slides and review the steps now that we've got that visual. I just think the visuals are worth $1 million here. Okay, so this is the steps of the action potential. Sodium gates open and sodium enters the cell, causing depolarization when the hill went up, right? Reaches +30, those shut, and now potassium gates open. Potassium flows out for repolarization. It becomes more negative. Okay. This action potential goes down the axon to that synaptic cleft. It only goes one way, because if it goes 2 ways, it would confuse the signals. Reaches the end of the axon, the synaptic cleft releases neurotransmitters. Those neurotransmitters go across to the receptor, whatever that receptor is, nerve muscle gland, stimulates that nerve muscle gland to do its thing. That's the basic gist of an action potential. So if you have any questions after you review this, let me know. Once again, I'm trying to give you just the basic gist of this because, like I said, I could teach action potentials for days. Okay. What happens after the electrical impulse is done? So at the synapse, it's kind of important to understand, after the neurotransmitter is used, a couple things can happen to it. The neurotransmitter can be destroyed by enzymes in that synaptic cleft, or it could be reabsorbed. And it could be reabsorbed by the presynaptic membrane, okay? I'm sorry, I find little mistakes with this book, and sometimes I have to correct them as I'm going through. So the reason it's important to know if it's being reabsorbed by the presynaptic membrane is there are some medicines that will stop that reabsorption and keep it in that synaptic cleft. That way it can continue to activate the receptor that it's trying to get to, okay? So neurotransmitters can actually be inhibitory. There are some neurotransmitters that will slow down activation of something. For example, parasympathetic stimulation to the heart. You'll release a neurotransmitter that will slow the heart rate. So just to realize that neurotransmitters can activate or inhibit because some medicines will work along those lines as well. Okay, some medicines will either increase or inhibit activities, just like, I think the heart is a good one to keep in mind because we have some medicines that'll slow heart rate. Okay. All right, so there's that action potential again. And here is where the action potential, and we reviewed this, but I think this is a good review. You can see that action potential coming down the axon. I'm just going to review it briefly. Again, I know I'm probably beating a dead horse, but I find repetition with these subjects are helpful. So this nerve impulse or action potential comes down the axon, stimulates the release of neurotransmitter, which comes across, attaches to receptors on that postsynaptic membrane after it passes through that synaptic cleft, and it will stimulate whatever this receptor is. Okay. All right. And you can see there's additional words, synaptic terminal, I'm not going to use. We know pre and postsynaptic membrane. Synaptic cleft, you need to know. I just called these receptors. Okay, these can be ion channels, don't worry about it. Okay, and then synaptic vesicles with the neurotransmitters. Vesicles are just a container for neurotransmitters. All right, and that, my friends, brings us to a question time. So an action potential is what makes muscles and nerves work. I told you I was going to beat this right? Beat this to death, so you really know this. So action potential is what makes muscles and nerves work. True or false? You're welcome. Answer that, and let's move on. Okay, so we're moving out of nervous tissue. You've got just some basics of nervous tissue. We're going to move into central nervous system, which is the main control center. So this is going to be the skull and the vertebral column, which is going to house the brain and the spinal cord. Okay. In the brain, we're going to have several structures we're going to talk about. One of the things I just wanted to introduce, and I'm going to show you pictures. I love pictures for central and peripheral nervous system. So I'm going to teach you all these anatomical structures for the brain on pictures. That's why I'm not listing them here. But I do want to talk to you about the generalities of the ventricles and the meninges here. So the ventricles are the spaces in the brain and somewhat down into the brain stem that produces cerebral spinal fluid, which is the fluid that will then flow down the spinal cord and around the spinal cord in the brain, and it provides some cushion and some support. So it's created in the ventricles, which are inside of the brain, but then it flows around the spinal cord and the brain through channels. And I'll show you these ventricles and these openings on a picture. The other thing to know is cerebral spinal fluid actually will fill the space between the meninges, known as arachnoid and pia. Okay, so that's important to know too, because if we were to get a bleed in the cerebral spinal fluid, we could get an infection in the brain or the spinal cord. And we're going to look at pictures of those meninges in just a little bit. Okay, the meninges are 3 layers of a protective membrane or membranes that encase the central nervous system, both the brain and the spinal cord. Dura mater is a very tough outer layer, and it actually reminds me of the consistency of a garbage bag. It's pretty tough if you pull on it, and it won't really stretch out. The next layer in is the middle layer, known as the arachnoid layer, and arachnoid references arachnid because it actually has a spider web-like consistency. The blood vessels are located here. So this is why if we get a bleed in that subarachnoid space, which is beneath the arachnoid, we can actually have more bleeding and we can have infection getting into that cerebral spinal fluid. Pia mater is the innermost layer, and it's actually right on the brain, and it's right on the spinal cord. If I were to dissect out a brain or a spinal cord, I would actually have to take a scalpel and scrape it to show you the pia mater. It's a single layer of cells that's right on the brain or the spinal cord itself. Okay, so let's get looking at some pictures, and I highlighted the structures that I want you to know. Okay, we are going to look at a better picture of meninges, but meninges are those layers that we just talked about. The cerebrum is simply the 2 cerebral hemispheres, right and left. They have multiple structures in them. We'll look at them one by one. The brain stem is going to be the connection between the brain and the spinal cord. Okay, and the brain stem includes the midbrain, and the midbrain is just going to be this space right here, the pons, and I always think of the pons as being the big fat belly of the brain stem. I was pregnant when I was teaching this, and it always reminded me of a pregnant belly. And the medulla oblongata is the expanded area that's just superior to the spinal cord. So midbrain, pons, medulla oblongata. And once again, this is going to be the connection between the spinal cord and the brain. A lot of processing will happen in the brainstem of essential functions of the body and also the transmission of signals, both sensory and motor. Now, the corpus callosum is this white matter right here. And we learned that white matter is primarily axons that transmits information. The corpus callosum is a very important structure because it allows the right and left brains to talk to each other. Our right and left brains have specific signals that only go to them. If we didn't have this connection of the corpus callosum, they wouldn't talk to each other and we wouldn't be able to coordinate activities and functions. So gyri and sulci are simply the raised areas. So gyri are these raised areas. Sulci are these depressed areas. And what those do, once again, if we think of waves, is they increase surface area. The final thing I want to talk to you about on this picture is the cerebellum. And the cerebellum is this entire thing that's at the base of the brain. It's also how I always orient myself to front and back of the brain. The cerebellum helps with coordination of movements. Here you can see the layers of the skull, which will encase the entire brain. It's pretty tight in there, guys. So this is an actual cadaver. There's not much space between that and what is called the dura mater. You could see this is the dura mater here. And if we were to cut that away, there'd be a thin spidery layer, which looks like arachnoid. And then right on the brain itself would be the pia. Now, you could see the raised areas, which are the gyri. You could see the indented areas here. You could see the blood vessels. You have blood vessels coming up to the brain, and they'll be interspersed throughout that brain matter, and that'll bring fresh blood to the brain tissue itself. Now, I wanted to point out what are called dural sinuses. So I want you to just listen for a minute. We have fresh blood that actually comes up through the carotids and what are called the vertebral arteries, but you know the carotids pretty well. They'll provide fresh blood to this brain tissue. The brain will then provide wastes that need to be gotten rid of, because don't forget, we need a lot of glucose and a lot of oxygen going to this brain tissue. After we use up the glucose and the oxygen, we're going to have wastes and carbon dioxide that need to leave. They go into what are called dural sinuses, and you could see them here and here. There are a lot more of them. I just want to introduce the concept. These dural sinuses then will drain into the jugular vein, getting rid of the waste from the brain. So, and they're kind of invested into the dura mater. That's why they're called dural sinuses, okay? So just as a side note, those dural sinuses will take away the used blood from the brain tissue, put it into the jugular veins. Here's the spinal cord as it looks in the vertebral column. And there are some things that I want to make note with this. So we'll look at this more in spinal cord, but here's the nerve roots that'll come out to make the nerves that go to the body. Okay, C1 through C8, T1 through T12, L1 through L5, and then we also have sacral S1 through S5. We're going to go over that in the future. What I want to talk to you about is with the spinal cord, there's a cervical enlargement, and the reason we have a cervical and a lumbosacral enlargement is because we need more nerves to go to the upper and lower extremities. The other thing that I want to point out is the end of the spinal cord is right here, and that's approximately at L2. So that is why we do epidurals below in this area. so we don't damage the spinal cord. You could see if they were to come between the lamina, which is just the spaces in the vertebra, at a higher level, they could hit the cord. So they like to go below that L2 level. I think they'll go as high as L3 because I have a herniation at L4, L5. That's where they did my epidural, was about L3, L4. Okay, so L2 is where the spinal cord ends. The nerves don't end though. The nerves continue down as a collection called cauda equina, C-A-U-D-A-E-Q-U-I-N-A, and it's called cauda equina because it's low and it looks like the tail of a horse. So cauda equina, collection of nerves that go to the pelvic basin and the lower extremity. Here are the ventricles of the brain. And once again, the ventricles are the spaces in which cerebral spinal fluid is created. And there are three groupings. There's two lateral ventricles, a right and a left. Okay, once again, I've highlighted what you need to know. We're not going to get into all the specifics. So there are two lateral ventricles, and that's why we jump down immediately to the third ventricle. Okay, the third ventricle is just about at the thalamus. Okay, we'll look at the thalamus in a little bit. So just put it into your head and we'll review it again. Third ventricle is around the thalamus. It sends fluid down through the cerebral aqueduct to the fourth ventricle, which is in front of the cerebellum. So we have the two lateral ventricles. There's always arguments as to what is 1 and 2, but don't worry about it. And then it goes down to the third ventricle and then the fourth ventricle. And then it comes down and it can either go down what's called the central canal of the spinal cord, or it'll go out through these lateral apertures. You don't even need to know the name, but it'll go out and to the outside of the brain and the outside of the spinal cord. I'm trying to draw it, but my drawing tool is delaying. Okay, so even though it's created in the center of the brain, we have the ability to send it out so it can go around the brain and the spinal cord. And it allows a little bit of cushioning around the brain and the spinal cord for protection. All right, so moving on to the lobes of the brain. These should look very familiar, I hope. I hope. If not, spend a little time and review. Okay, and they're named according to the bones under which they sit, or vice versa. Just so you know, the bones on top will be named the same names. We have frontal lobe. Okay, and once again, the cerebellum will be at the base in the back. And then we have the brain stem and the spinal cord. The temporal lobe will be near the temporal area. At the top, this blue area is parietal lobe. At the base above the cerebellum is occipital lobe. Now, the central sulcus separates frontal lobe. And the reason I put this is because we have motor in the front here, sensory just behind it. For the most part in the brain and the spinal cord, motor will be towards the front, sensory will be towards the back. Are there some exceptions? Yep. But the majority of it will be separated by the central sulcus. Motor of the body and the face will be to the front. Sensory of the body and the face will be to the back. Okay, and we'll go over which lobes have which basic functions in a few slides. I'm just trying to give you the general anatomy. Here's the spinal cord. So once again, here's our meninges, which are also on the spinal cord. And you can see they have them labeled. We have dura on the outside. Okay. Underneath the dura mater, we have the subdural space. That probably sounds familiar because we can get bleeds in there, which I have in the notes in the future. But I think this is a great picture to see these We have the arachnoid mater. And just underneath that, or deep to that, you have subarachnoid space. That's where blood vessels are. They actually have blood vessels pictured there. And that's why this subarachnoid bleed could really be an issue, because you can bleed more, and then you also can put it into the cerebrospinal fluid. because that's where the cerebral spinal fluid is. It's in that subarachnoid space. On the cord itself is pia mater, which I mentioned previously. It's just a layer of cells that are actually on the brain and the spinal cord itself. Now, we also have white matter and gray matter. I'm just pointing that out because gray matter is collections of cell bodies. This is where we process information. White matter is where we transmit information. Okay, we're going to review that again in the future. Now, here's a spinal nerve because we're actually on the spinal cord. Spinal nerves will carry sensory and motor to and from the body. Okay, the back of the cord, just like the brain, and this is actually the back because it's dorsal, is going to be sensory. Anterior is motor. Just put that in your brain. We're going to go over it again. But the reason I'm pointing it out here is because the anterior is motor, the posterior is sensory, but they come together to form this spinal nerve. And in the spinal nerve, we're going to have both sensory and motor going out to the body. Okay? And then this points out the 3 layers of dura mater. And that brings us to a question, and this is a fun little let's practice. And I want to go through these one by one. So, the top one. Actually, I'm going to have you take a minute because I can't go between drawing and moving things. I want you to pause the tape, do a little list, and I want you to list the structures. And I'm going to start at this upper one here. I think if I highlight it, oh, that's how I can do it. Okay, I think it highlights it if I do it like that. This is the first one we're going to do. If you want, you could pause the tape and do all of them. So what does this represent? This could be a couple things. So think about it for a minute. And we're looking at lobes. This is going to be frontal lobe. Could also be gyri, could be cerebral hemispheres. So if you guessed any of those, that's fine. Moving to the right, this one that I've just clicked on, what lobe would this be? If I move that, that'll be parietal. How about this back one? What lobe would that be? It would be occipital lobe. Once again, it's also pointing to gyri. I'll be very specific. If I ask you a question on an exam, I would say, what is this raised area, for example, or what is this lobe? This would be the specific area, would be the cerebellum. This specific area would be the what lobe? Temporal lobe. This general area would be the brainstem. Okay, and just below it is the spinal cord. All right, we are going to move into the next section in the next video. If you have any questions, let me know. This is a chunk of change doing the nervous system, but it's great information. So I will see you in the next video.